Is anyone presenting the student research symposium today?
What?
Is anyone presenting the student research symposium?
I'd like to, but I never had anything. So.
Oh, well, there's always more. And you don't necessarily need publishable data. Oh, was it required or? All right, lights okay?
Yeah.
All right. So, student research symposium. If you ever have a chance, that's a great thing. My first research presentation was in that context. It's great. So if you guys do research next year, probably consider doing it. It's fun. Plus, I'm a judge, so you might actually be forced to talk to me about your research for 5 minutes. So on Wednesday, we talked about the effect of substituents on our benzene ring, particularly electron donating groups and electron withdrawing groups. The take-home message was electron donating groups, such as methoxy groups, or amines, or even methyl groups, do two things. One, they dump electron density into the system, making the pi system more nucleophilic, and hence speed up the rate of electrophilic aromatic substitution. The other thing they do is, by the way that they dump electron density in the system, the electron density they dump in resides at the ortho and para positions, as given by these partial minus charges. So electron donating groups direct the electrophilic aromatic substitution to the ortho positions as well as the para positions. And you can explain this using resonance. And I drew resonance structures of each of these and showed you that the partial minus charges in the various contributing resonance structures reside in the ortho and para positions. So definitely be able to draw resonance structures of these aromatic groups and use the resonance structures to explain the regioselectivity of the reaction. By the way, those who showed up, if anyone showed up to my office hours early, I showed up 5 minutes late because I was judging. So if you left because I wasn't there, I apologize. I think I got there 5 minutes late, so I apologize to anyone who missed me at my office hours. So electron donating groups, ortho-para, faster reactions. Electron withdrawing groups, slower reaction, because electron withdrawing groups like nitros or carbonyls, via resonance, withdraw electron density from the pi system. In essence, stabilizing the pi system, because electron delocalization equals a stabilization event. And since these electrons are more stable because of the electron delocalization effect, they are going to be less nucleophilic. Because remember, nucleophilicity is directly correlated with the energy level of the electrons. And so when we have a delocalizing stabilization event, that's going to stabilize the electrons and make them less nucleophilic. And that's why for electron withdrawing groups, the electrophilic aromatic substitution is slower, because the electrons are more stable. And thus, since they're more stable, it's going to need more energy to do it. Energy and time. So they're slower because of that. And electron donating groups are faster because pumping in electron density in the system is raising the energy level, because there's more electron density in the confined space of the aromatic system, so there's less delocalization. So higher energy, more nucleophilic. The other thing electron withdrawing groups do is they deactivate the ortho and para position. And again, you make this argument the exact same way through resonance. And I did this on Wednesday, so I won't do it again. I'll leave that for your studying. Because again, being able to explain the regioselectivity with resonance will be on the exam. Obviously, it's a key part of chapter 15. You draw your resonance structures, and you can see in the resonance structures, you have a partial positive charges at the ortho and para position. And since they're partial positive charges, those positions are going to be deactivated, right? Because this electrophilic aromatic substitution requires the carbon pi system to act as a nucleophile. And if you have a partial positive charge, you're going to be less reactive. So for that reason, the meta positions are where the electrophilic aromatic substitution will occur with electron withdrawing groups, because the meta positions are fairly untouched. And again, you can show this through via resonance structures, as I did on Wednesday, and definitely work in that. So that was the meat of the lecture on Wednesday. I ended lecture talking about other groups, namely halogens. And so halogens are more electronegative than carbon. Thus, halogens like chlorine or bromine are technically electron withdrawing groups. So, hey, in the videos, does green come up well, or does green kind of stink?
It'll
be fuzzy?
It's up to you.
All right, I'll only use green when I have to then. Did orange come up okay? Those who have watched it? All right. So for halogens, halogens like chlorine and bromine are weird substituents. Since they're electronegative, they're electron withdrawing. So chlorinated and brominated arenes, aromatic systems, will be less reactive. So chlorinated and brominated will be less reactive than, say, benzene. So chlorinated and brominated aromatic systems are less reactive because chlorine and bromine are electron withdrawing groups. But they're different than other electron withdrawing groups. So whereas things like nitro and esters and other carbonyls will be meta-directing, halogens, while they are still electron withdrawing, are actually ortho-para-directing. From Wednesday, why are halogens, which are electron withdrawing groups, ortho-para-directing? Yeah, the lone pair of electrons are able to dump into this system through, and I drew those resonance structures, but remember resonance structures are nothing more than mnemonic. I drew the resonance structures that show that these electron densities, the electron density from the lone pair of electrons can dump into the system, giving us a partial negative charge that can resonate to both ortho positions and the meta position. So whereas chlorines are electron withdrawing, they're ortho-para-directing because the lone pair of electrons on the halogen can influence, can act similarly to what we expect a lone pair of electrons in the oxygen to do. So whereas the chlorine is net deactivating the system through electron withdrawing effects, the lone pair of electrons will make the ortho and para position slightly more reactive than the meta position. So we get a slower reaction that occurs ortho and para, and that's because of the lone pair of electrons and the halogen. So halogens are paradox. This is the oldest joke in the book, but I'm compelled to share it. So halogens are paradox. So what is this? By the way, this is in Professor Smith's office. Paradox, right? PhD paired to another PhD, paradox. That's a very punny joke.
I see what it is.
The joke's older than my clothes, so older than my style, I guess. But since I'm going to be a father in, 6 months, that means my fashion has to freeze the second my kid's born, right? To keep the father-style paradox. So, in other words, halogens are paradoxes because they're electron withdrawing groups that direct ortho and para. Yes?
So you'll end up getting more para product because of the induction of
Yes, exactly. Exactly. That being said, to be perfectly honest, most of these directed electrophilic aromatic substitutions we showed you gave you 2-to-1 and 3-to-1 mixtures, right? In chemistry, a 2-to-1 and a 3-to-1 mixture, that's not that great. If I get a 2-to-1 mixture, I'm like, well, it's basically equal, because then you have to purify it away. And so, for major products, the safest thing to do is to say, all right, it's going to be ortho-para directing, so we can get the ortho and the para. There are certain cases I will discuss where it will be pretty obvious what the major thing will be, i.e. via sterics. And sterics can have a role in ortho-para stuff, but the sterics have to be massive. I'm talking about, and I'll show you examples today, I'm talking like T-butyl groups, or things that are obviously forming these huge steric interactions. A methyl group is going to have a much smaller effect. A methoxy group is going to have a very small effect sterically. So the thing that dominates those are going to be electronics. But actually that gives me a great segue to my next thing. And so the only thing I haven't explained is the methyl group. So I'm going to finish up by explaining why a methyl group is electron donating and why it's ortho-para directing. And then that will allow me to compare to the T-butyl group and explain ortho versus para with those. So that's some great segue. So halogens are paradoxes because they're electron withdrawn but ortho-para directing. Last thing I will talk about is the directing effect of alkyl groups. And I'll show you the first example with a CH3 or a methyl group. So methyl groups are electron donating. Is anyone going to tell me why a methyl group or any alkyl group is electron donating? Yes?
Would it conjugate the pi system, the empty orbitals?
Absolutely. Well, the
CH
sigma bond
Yeah.
will hyperconjugate.
Yeah, hyperconjugate.
So hyperconjugate is the term we use to explain why tertiary carbocations are more stable than primary carbocations. And so the reason alkyl groups are electron donating is the exact same reason for why tertiary are more stable than primary carbocations. And that's because I'm going to draw my pi system. All right. And so here's some in black is our aromatic pi system. So each of these orbitals share 6 electrons because they're aromatic. This carbon-hydrogen bond, the sigma bond, the electrons in this sigma bond of this carbon-hydrogen, so there's 2 electrons that are doing blue, this bond is able to rotate so that each of these carbon-hydrogen bonds is exactly parallel with the pi system. And what happens when orbitals are parallel to each other? You have orbital overlap. And when you have orbital overlap, electrons can flow. So just like in this case with the tertiary carbocation, so here's our MTP orbital. Here's one of the hydrogens and the substitution of our cation. So whenever I draw this, right, I'm usually saying it's either a bonding pi orbital in an aromatic system, or I'm saying it's an MTP orbital. So in this case, this is an MTP orbital. Right, and so tertiary carbocation is more stable because the electron density from this bond can rotate so it's perfectly parallel with this pi system. Empty pi orbital in this case, I can dump in. And this can happen 3 times, right? We can have it so we have 3 different carbon-hydrogen sigma bonds, carbon-hydrogen sigma bonds that are perfectly parallel to the empty pi orbital, so empty pi orbital. So these are able to overlap perfectly with it. And so now we have donation of the electron density from the carbon-hydrogen sigma bond into the empty pi orbital. So sigma to pi donation that stabilizes the empty pi orbital. And this is what we call hyperconjugation. And so in the pi case, it's the exact same thing. The overlap of this carbon-hydrogen sigma bond with now the bonding aromatic pi orbitals of the pi system means that the electrons from this bond can flow into the system, giving electron density into it and making it more electron rich. So alkyl groups or electron donating groups, because of this sigma to pi overlap that allows these sigma bonds of the carbon-hydrogen bond to donate into it. Is this a bigger or a smaller effect than resonance? So smaller, right? So compared to this, which electrons are going to donate into the pi system better? Out of the methoxy? off of the methoxy or off of the methyl group? These electrons, right? Because these electrons are lone pairs. They're non-bonding. Non-bonding electrons are going to always be easier to donate than bonded electrons. So methoxy groups are much more electron donating than alkyl groups. But alkyl groups are still electron donating, and just realize that's because of this hyperconjugation. So a methyl group will give you a mixture of ortho and para products. And you get roughly maybe a 1-to-1 or a 2-to-1 mixture of ortho to para. But in a test, you would just draw both the ortho and para because there's not much differentiation energy-wise. And so a methyl group will give you both ortho and para. So if you were to take toluene, so methylbenzene, and do a sulfonylation using SO3 and H2SO4, we will get a mixture of ortho, sulfonylated toluene, and para, sulfonylated toluene. So we get a mixture. Reaction will be faster than benzene because methyl is electron donating. So think of benzene as a reference. So with benzene we call 1. We know from the other day that methoxybenzene will be about 1,000 to 10,000 times faster than benzene. So replacing a hydrogen with a methoxy will be about a 10,000-fold increase. Replacing a hydrogen with a methyl group will be about a 1,000-fold increase in rate compared to just having our hydrogen where a methyl group is. So again, methyl will speed the reaction up, and it will direct ortho and para. But now let's get into sterics. So let's go now, and I'll do it in orange. So what about, let's do something much bigger than methyl. Let's do a terp-butyl group. So is this terp-butyl group, so a carbon between methyls, is this electron donating group? Absolutely. Because just like in this case, we have the carbon-hydrogen sigma bonds donating, a carbon-carbon sigma bond can also donate. So an sp3 carbon sigma bond is going to be a similar sigma donating ability as a carbon-hydrogen. So absolutely. This can the electron density in a carbon-methyl sigma bond can raise the HOMO or dump pi electrons into the pi system the same way a carbon-hydrogen bond can. So yes, this is an electron withdrawal group. So if we do the same reaction, a sulfonylation, actually, so we get some review. I don't want to do a sulfonylation. Give me an electrophilic aromatic substitution. Just throw out a functional group, any functional group. Someone say, was that nitration?
Yeah.
All right, so nitration, we take nitric acid and sulfuric acid. So with methyl, we get a mixture of ortho and para. With the much bigger terp-butyl group, do you expect to get a mixture of ortho and para?
Yes.
More para. All right. Yeah, I like more para. I think if you said only para, that's fair, and I'm good with that. But what do scientists like to do? We like to cover our bases. You will almost never see a scientist saying something is absolutely true. Like when I tell you guys mechanisms, you'll notice I don't say this is absolutely the fact. I'll say this is mostly 99% true. I always like to have that 1% of wiggle room. Unless I'm done with my wife, and then she's the most awesome person I've ever known, bar none. Hopefully she doesn't find this on YouTube. Maybe I hope she does. So in this case, because of the sterics, we are going to be precluded from adding at the ortho positions. So when you have a really big group, like a terp-butyl group, now we will get mostly, almost entirely, para substitution. almost entirely para substitution when you have a big, bulky group. So, from that point, the chapter ends with some chemistry that I don't think is particularly important. It talks about benzylic halogenations, but benzylic halogenations we already talked about, right? Benzylic halogenations are just radical halogenations. I think I may have had a question in the last exam on benzylic. So since we spent a lecture talking about allylic halogenations, just realize the mechanism for benzylic alkylations is identical, just the benzylic weak CH bond rather than the allylic CH bond. The one thing I will mention, so what my plan for the rest of the lecture is, I'm going to talk about the last piece of chemistry, and then we're going to get into synthetic examples of electrophilic aromatic substitution. So just bear with me one quick second. So, does anyone know what this molecule is? It's a common name, I know you've heard it. This is styrene. This molecule is styrene. And so any aromatic system that's connected to a double bond is from a class of molecules called styrenes. Based on the name, does anyone want to tell me what styrenes are most used for? Styrofoam, polystyrenes. Styrenes are great things to make polymers with. And hopefully later on, maybe chapter 17, I'll spend 20 minutes talking about polymers and showing you the difference in structures between things like nylon and Kevlar and Mylar. And here's the spoiler alert. Kevlar, which stops a bullet, is not that dissimilar from Mylar, which we make balloons with. So it's amazing what these subtle changes in chemistry can do to the properties of a polymer. But yeah, so this is styrene. So the interesting thing about styrene is it's a double bond. And you can do your typical double bond chemistry tool. So which of these pi systems is going to be higher in energy? The double bond, right? Because it's not aromatic. So if we take H3O to do an acid catalyzed hydration, and you know what, I'm going to make this tricky. I'm going to put a methyl group here to illustrate something. So benzene, double bond, methyl. So which of these pi systems is going to react and act as a base towards the H3O? The aromatic system or the just pi system? The pi system, right? This is going to be much more reactive nucleophilically than this because these protons are stabilized because they're aromatic. So we take the proton, and this is going to be Markov chemistry. So which carbocation are we going to form? Is the carbocation going to be here, or is the carbocation going to be here?